the next speaker is Kathleen Kohn from KTH, and she's going to talk about geometry of neural networks.
Yeah, so thanks a lot for the invitation, and also thanks to Bernard for the great previous talk. So I'll try to keep up. So this is, yeah, so let me tell you now a little bit more specific again about machine learning. This is joint work with, well, mainly this is joint work with Johan Brunner and Matthew Drager, the first two that you see here. And I hope I get to also talk a little bit about joint work with Guido Montufar and his student Thomas Merck. But this is not yet finished work, so I will not say as much as I wanted to say. Yeah, because I thought we would possibly be further in the progress at this point in time. But anyhow, this talk is somehow like a combination of some talks we saw yesterday by concepts from Paul Breiding's talks will appear, and Joe Khalil's, and also Ting Ting Tang. And yeah, so I will not waste so much time on defining neural networks again. I am here also only dealing with feed-forward networks. And if you have any question, always just interrupt me and feel free to ask, of course. So somehow machine learning and these neural networks fit in somehow the more general framework of parameterized learning, if you want. So a neural network is essentially just a continuous mapping, as you see, from the space of weights and the input space to the output space. And for a case of neural networks, it has to be of a certain shape, of course, that we have seen in talks yesterday already. And so what's also a central concept that appeared yesterday, most notably, I think, in maybe Joe's talk, was this function space. I forgot what exactly Joe called it, functional variety, or let me call it a neuromanifold here. So that is the object you get when you vary the weights, and for each fixed weight vector, you consider the function from input space to output space that you get. And so the family of all such functions, that is well, the function space that the neural network can somehow parameterize, and that's sometimes called the neuromanifold. So there is some easy observations we can make about this object. The first observation is somehow, if we assume that this continuous mapping phi is piecewise smooth, then this neuromanifold deserves its name in the sense that it's going to be a manifold with singularities. So very often not a smooth object, though. And also, although this is an interesting object in the sense that it lives in an infinite dimensional space, namely the space of all continuous functions from the input to the output space, the neural manifold itself is finite dimensional since it's parameterized by the possible weight vectors. So that is the object of interest that I want to focus on here, and that is essentially trying, if you study this object, you're answering the expressivity question in machine learning, like giving a certain network architecture, what functions can you get? So the running example for this talk is linear networks. So in some sense, I'm doing what Joe did just in the baby case. This is really the very first thing to study, and most theoretical works that can really prove very cool things are somehow on linear networks. And beyond that, it gets very hard, as we have seen, to understand things theoretically. But there's good progress. Anyhow, let me focus on linear networks. So in this case, this mapping phi is just matrix multiplication. And then you multiply the result with the vector x, which is the input vector. So our weight vector is just naturally a tuple of matrices. And then I multiply all of those together and with the input vector x, and then that's my linear network mapping. And what is the neuromanifold in this case? Also that we have seen already yesterday as an example. It is exactly the set of all matrices of bounded rank. Right, so this matrix M that I write here is just the product of these W matrices. And so if you factor matrix as a product, then of course its rank is bounded. And in fact, this is like an if and only if you get all matrices whose rank is upper bounded by this minimum here. And since this minimum is such a long thing to write, I will always write R for this maximal possible rank. So one thing what we somehow wanted to achieve with our article, somehow not just writing yet another article on linear networks, but focusing and not just proving things that people observe, but really understanding why people prove things a certain way and why you expect things to be true and why do you expect other things not to be true, and give geometric intrinsic reasons for that. And sometimes it's a little bit hard to say if there's technical proofs what exactly is going on. And so we try to make this more geometric. And so there's lots of geometric concepts I'm just wanting to advertise here. So for instance, there was also these assumptions that we have seen in, I think in Ting's talk, for instance, that I will get back to in a second. Not sure if this one was there, but so one assumption, for instance, that people might do is write something like this, that this rank R is equal to the minimum of D0 and DH, right? So this technical assumption just means that if you consider which layer in your network is the smallest one, then that one should be an input or an output layer. And in that case, this neural manifold is very easy. It's actually just a vector space of all matrices, right? Because the rank is not actually bounded. And so this is what we call a filling architecture, as in Joe's talk also. And yeah, so the second case is then what we will call a non-filling architecture. That happens if this rank is smaller than the minimum size of the input and the output layer. And in that case, this neural manifold is not a vector space anymore. And that's why we call it non-filling. It is actually an interesting thing to study, and namely it's the determinant variety, which we know is a classically studied algebraic variety. And yeah, so for optimization, it's of course relevant to note is that this thing is neither convex nor smooth. And so it is actually a relatively, possibly a difficult optimization problem that you want to study here. So that's the first concept that I want to advertise, to somehow distinguish also when you have more complicated network structures, to distinguish what geometric shapes your manifold can have and if you can somehow put it into classes. And this filling and non-filling idea, I think, is a wide concept that one can do in many other more complicated settings. Okay, again, if you have any question, please always interrupt me. Otherwise, now we have somehow looked a little bit at the static geometry of this neural manifold. Now, what we do, of course, in machine learning is we want to optimize something. And there's where this loss function comes into play. So the loss function is this concatenation of two functions, where mu is just the parameterization that eats a weight vector and then outputs the corresponding continuous mapping in the neural manifold. And then the small l is some functional that is at least defined on the neural manifold. And that's what we want to optimize. And there's this beautiful paper that I encourage you to have a look at if you have time, with visualizing the loss landscapes of several neural networks that are used in more practical scenarios than just studying linear networks. And so these loss landscapes can be pretty wild, as you see. And there's many geometric questions you might want to ask about them. For instance, the first sort of observation that you can do is if you have a a critical point of this function in L on the actual neural manifold, so that's the algebraic problem we want to solve, then of course, every point in the fiber under the parameterization map mu is a critical point of this composition of functions, of the loss function capital L. And so what does that mean? So somehow in theory, we might be interested in studying this left problem, like optimizing small L on the neural manifold. But what we in practice do when running algorithms is doing this in the parameter space. And for any critical point on the neural manifold, we typically have infinitely many critical points in the parameter space, since neural networks are typically over-parameterized. And so we are going to find one of these infinitely many parameters. It might be interesting to study if you can, for instance, walk inside this fiber. And can you go to different parameters? They, of course, give the same function, phi, but they might have different numerical properties and different numerical stability things, I mean here. So it might be interesting to study this question, and so I propose it as a question to study in other scenarios. So for linear networks, that would be my baby example here. We looked a little bit at this question. So here, the loss function is of this form that it's the parameterization map mu is just a product of, it takes a product of matrices. It's a matrix multiplication map, of course. And recall that the neural manifold is just the determinantal variety. So what we can do, we can somehow give some topological information on these fibers. So we can somehow characterize how these fibers over critical points give connected sets. And in fact, it's so that typically for a critical point on the neural manifold, its fiber has many disconnected parts. And I can make this a little bit precise. So whenever you have a matrix on your determinantal variety that is actually of the largest possible rank, then the fiber under the matrix multiplication map has 2 to the b, so exponentially many possibly, path connected components. And that exponent b counts how many inner layers have the smallest possible width. Right, so R was the smallest width appearing in the network. Now for a moment I ignore the input layer and the output layer and only look at the inner layers, and then I count how many have that small width. So it's particularly bad if you do something like an autoencoder. I can't draw it for some reason on my iPad here, but it's particularly bad if you think of a situation where the input layer is large and the output layer is large, and you have some autoencoder where all the other layers in the middle are small and have the same size. Okay, and then you get many, many components. Then it's somehow better to have an autoencoder with just one tiny layer in the middle somewhere. Okay, and though, I mean, sometimes it depends on your application, right? The result you're getting or you're looking for might actually be a lower rank matrix. And in that case, this fiber is actually path connected. Okay, so that is one question I encourage that can be studied in more complicated scenarios than linear networks, studying the fibers of the parameterization map. Now let me come to another geometric concept that I want to emphasize and that we somehow want to emphasize with our article, which is this distinguishing between what we call pure and spurious critical points. And one motivation was because there's lots of slang around, of course, and for instance, the term bad minimum is somehow overused in different concepts. And so what we call a spurious critical point sometimes is called the bad minimum, but we don't like it very much. So let me first tell you what we think of when we think about these words. So we call a critical point of the loss function capital L pure if it actually comes from a critical point on the neural manifold. Right, this is of course somehow the points, the way we set up the problem, that is the points that we actually want to get. And all the others that we might have, those is what we call spurious. Because in some sense, this is not how we set up the problem in the first place. We kind of do not really want to get them. They're spurious because they come only from the choice of parametrization. Right, so that's somehow our intuition, because the neural manifold is one nice object to study, and there might be many different parametrizations giving the same thing, and that might influence what critical points you get, of course. So using this notion, one observation you can make is that spurious critical points, for instance, often or somehow typically have the property that in the same fiber, there's other points that are not even critical. So if I would have, I might end up finding something when I run my training, then I might find a weight vector that says, oh, this is a critical point. But in the end, it might not be a actual critical point that we're interested in, because a different choice of weight vector would have given me a non-critical point. And again, if this is confusing, you can just interrupt me if you want. Okay, so this is just some very basic differential geometry that I want to summarize, and it just follows from the definition. So if you consider the differential of your parametrization map and at a critical point, and the differential has maximum rank, then it has to be so that the critical point is a pure one. So that is one nice criterion to see which points might be pure. And what is even nicer, right, in that case where our differential has maximum rank, we can see, of course, something much, much stronger, namely the type of the critical point in the parameter space is the same type it has on the neural manifold. Like if I take the image under the parametrization map. So this is a fairly easy thing to see, but it's incredibly useful. So let me tell you why. So for linear networks, we worked out explicitly what is a pure critical point, what is a spurious critical point. I'm not telling you all the details here because this sort of yoga is then a little bit technical, and I want to highlight the geometric ideas. But what you get out of this is some sort of discussion on this sentence here. So sometimes you hear, or we have heard this a little bit, not exactly in these terms, but that for linear networks, the loss function often has no bad minima. And again, here the bad minimum means something else. These are local minima that are not global. And so somehow you, of course, would prefer if you work in a situation where you don't have them. Because then if you end up in a local minimum, you would know that you actually found a global one and you're very happy. So this sentence is partly true and partly false. And I want to explain somehow the geometric reason for why that is so. So using this distinguishing between pure and spurious critical points and this easy proposition on the previous slide, you can prove a rather powerful proposition that is very specific to linear networks, which is that is actually true for linear networks, that you have a bad minimum in the parameterized problem if and only if you have a bad minimum on the neural manifold. So if you want to study the question if linear networks have bad minima, then we have somehow reduced it now to the question if optimizing on the determinantal variety has bad minima or not. But as I said, this is, I think, very specific to linear networks. I don't think that this proposition with the strong if and only if is true for other activation functions, but that's an open problem. Okay, and so this proposition now is something I think that we have seen in talks yesterday. An immediate corollary, just now in different terms, is this corollary by Lauren and von Brecht, which is that if I am working in this filling architecture case, remember that meant that the neural manifold is just a vector space. And I am optimizing a convex function, then of course all local minima are global, right? Because I have a vector space, a convex function, there's just a unique minimum, so everyone's very happy. And so this is results that quite celebrated from 2017 somehow follows very easily from these geometric observation and our distinguishing from these pure and spurious critical points and the proposition above. And there's this maybe even more celebrated result that we also have seen in talks yesterday by Baldi and Hornig from 89 or Kawaguchi in 16, namely that if I'm working with the quadratic laws, then it's also true that all local minima are actually global. So this is also a corollary of this proposition, but it's not as immediate. And I will spend the rest of the talk telling you how you get it as a corollary. But again, if there's any questions up to here, that would be a good time.
I do have a question. Can you hear me?
Yes, I hear you.
Okay, so this is my first lecture that I'm attending from this lecture series. So this might have been answered in a previous lecture, but I'm wondering whether this this map mu, like with domain and target space, has a structure. If there's a generic fiber, say, my question is this map mu a bundle map away from a few critical points? Is this in general true, or is it much more complicated in general? And you cannot say such a general statement.
I mean, this is a good question. I mean, wondering what generality you mean, right? Because if you have some, I mean, in typically, this is just a matrix multiplication map, so here it's easier, but typically these you have this activation function in between each matrix multiplication, and I don't know. I mean, I think this would be, I don't know. Maybe someone else has an answer who has thought about this. I don't know.
Because if it were a bundle map, you, for example, could also look at the homotopy groups and you use the long exact sequence for bundles and stuff like that. But I'm not sure if this is even way too technical. Thank you. Yeah,
no worries. I mean, I think it is, as general, I think it is very interesting to study this map and study its fibers and study whatever structure you can find. But of course, I mean, in practice, the activation functions I use can be very wild, and then I doubt that something like that is true. But maybe in this setting that Joe explained yesterday, like I think maybe the talks will be uploaded or something. I don't know. Yeah, anyhow, other questions?
Yes, question. So in practice, what are these loss functions used for the practitioners?
Okay, I can show you this in a sec. I can show you this on the next slide, I think. Yes. So this is somehow the setup actually. So what you would somehow get is you would have training data. I think that also appeared in some talks before. So you have input vectors X and output vectors Y. This is training data, and I collect all these are pairs of training data, yeah, input output pair. And now I collect them into matrices. So X, the columns of the matrix X are the training vectors on the input side, and then the columns of the matrix Y are the output training vectors. And what you want to do is you want to find the best function in your neural manifolds that in the sense that it should approximate the training data. That's what it's used for. So if I'm having here the example of this quadratic loss, then what the loss does, it just in my case, right, my functions on the neural manifold are just linear maps. So I can just take such a matrix M, and then I want to see that M should preferably map any vector X to the corresponding vector Y in best case. So you want preferably that M times X minus Y is as small as possible. Does that answer your question?
Yes, thank you.
Yeah, so and this is, of course,
Kathleen,
more complicated.
4 minutes left.
Okay, I thought it's until 20. Was it not up to 16:20?
It's a 40 minutes talk, and we started 2-3 minutes late. So
Yeah, so I started at 15:40, so I have until 16:20, which is 12 minutes for me in my time. Maybe I'm wrong.
I think it's.
But I think I talked for less than half an hour now, but I can also stop earlier if you want me to. That's fine. But I don't have a specific goal where to get to. But
Let's try 5-6 minutes at least. Then we'll need at least 5 minutes break.
Because I also think there's a coffee break afterwards. But anyhow.
Yeah, maybe. Yeah, it's okay. Yeah, you are right. Sorry, I think I was confused with the different time zones. Yeah.
People say that I have 12 minutes, so I will take my 12 minutes. But
sorry,
again,
ahead,
like I'm more interested in questions than talking. So if there's more questions, I'd be happy to answer them.
Yeah, you have still 12-13 minutes. Sorry about that.
Sounds good. Okay, so this is what this loss function is used for. So that's why. So somehow I think the questions that one can answer as an algebraic geometer is maybe somehow one's on the static side, like study the neural manifold, or in Ting's talk, study the variety of critical points, like study this loss landscape. But this other question is, for instance, now I give you a loss function, I give you training data, and now you have an optimization problem to solve. And what can we say about this optimization problem, which is some sort of more dynamic question? But we maybe meet also differential geometry, I think, in more complicated settings. But so anyhow, sticking to linear networks and this quadratic loss, one observation you can make is this very easy observation here. And it looks like I haven't done anything, but so I assume for a second, a similar assumption to Ting's and one side of Ting's talk. If X transpose is the identity, that's sometimes called whitened data, then the loss function up to constants doesn't depending on M, I can rewrite it like this. So it is just M minus Y times X transpose, and then the Frobenius normal squared. And so why do I rewrite it like this? Because in this, it would mean that minimizing the quadratic loss on the determinantal variety is actually equivalent to solving the problem of minimizing the Euclidean distance of this fixed matrix Y times X transpose to the determinantal variety. And that is, of course, a problem we have seen, for instance, in the very first talk yesterday by Paul. That is, quite well studied at these days. And so this observation is not just true if XX transpose is the identity. It's enough to assume that XX transpose is invertible. And then you can write a similar thing. It just looks more technical, and that's why I didn't want to do it. But so that is, again, for me, somehow the geometric intuition of why people make this assumption, because then, well, the proof works, but most of all, this loss problem is just Euclidean distance to the determinantal variety. Okay, so now we are at this problem. Now I can give a short repeat for those who have not been in Paul's talk, which is a more general problem in algebraic geometry, which is if you have any sort of real variety, then there is some constant called the Euclidean distance degree, such that for almost all points Q, the problem of minimizing the distance from Q to the variety has delta many complex critical points. And we have seen this already yesterday. So here's my baby examples. If my variety is a point, then this number is 2, right? Because for almost every point, there is exactly the closest point on the circle and then the furthest away point on the other side. And there is no other critical points. But if you have an ellipse, I think many have seen this picture before, this Euclidean distance degree is actually 4. And so here in this picture, you see 2 points, one in the middle of this diamond shaped thing, where you actually have 4 critical points. And then I chose another point outside of the diamond, where you see only 2 critical points because the other 2 are complex conjugated pair. And another important notion in the story is that there is some points, data points, if you want Q, for which there is not the expected number of critical points, and that's called this the discriminant or the evolute. Yeah, here in the ellipse case, it's this beautiful diamond-shaped thing, and in the circle case, it's a degenerate thing over the real numbers. It's just a point. And I'm bringing up these 2 examples, although they might be boring to many people, because what I want to advertise is that determinantal varieties look like circles. They do not look like ellipses. And I want to say in the last minutes what that means. So what is happening for the circle is that the CD discriminant degenerates 2 points. Over the complex numbers, though, it is still a hypersurface. We just don't see these other points. And that's also what's happening for determinantal varieties. And that is essentially the geometric reason why there is no bad minima if you specifically work with the quadratic loss. Okay, because also I think the Eckert-Young theorem has been mentioned yesterday, at least by Joe, and so let me maybe restate it in some algebraic way, which is for determinantal variety. If I have a generic enough data matrix Q, so Q is the matrix that I have given, and I want to find the closest matrix on the determinantal variety, then this optimization problem, I can easily compute these number of complex critical points. It's a nice binomial coefficient. So that number is then, of course, the ED degree. Moreover, all these critical points are real, which tells us actually that this ED discriminant, as in the circle case, has codimension at least 2. In fact, it has codimension equal to 2 over the real numbers, and is in fact the matrices with at least 2 coinciding singular values. And finally, another important part for machine learning of Eckert-Young theorem is that this optimization problem has a unique local minimum. And I can easily determine from the single value decomposition which one it is. And that is, for me, the reason why this celebrated result is true. Because if I have a linear network and the quadratic laws, then what I want to say, there is no bad minima because I'm in fact just applying the Eckert-Young theorem. And there is just a unique minimum. Okay. And so that was somehow some arguments for why this sentence is true, that, well, often, I don't know, in certain applications, linear networks have no bad minima, but they can have them, of course. And for that, I want to mention this notion of generic Euclidean distance degree. So there's another constant, such that when you apply a random linear coordinate change to your variety, then compute the ED degree, then that is going to be that constant. So I think many know this concept here, but for those who don't know, it sounds a little bit confusing. So let me just do the example. So if I start from a circle that has ED degree 2, but then if I perturb the circle, I will get an ellipse. And that has degree 4. And for almost every linear perturbation, I'm going to get an ellipse that has this ED degree 4. So the ED degree of the circle is 2, but the generic ED degree is larger, it's 4. And again, I wanted to say that determinantal varieties look like circles. And that means if I would perturb them, I'm ending up in a more complicated situation, as the same is true with the circle. And why is this relevant to our machine learning question? Because I can also equivalently interpret this number as the ED degree. If I fix the neural manifold, I fix my variety, but I'm perturbing the distance. So instead of working with the standard quadratic loss, I'm working with some perturbed version of the quadratic loss. And now I'm just doing this example here. So if you do this, for instance, with the rank 1 matrices and 3 by 3, you see there's a considerable difference between these two numbers. And also this ED discriminant actually does become a hypersurface, which means that you have different numbers of critical points in different open regions. Like not every critical point is real anymore. And it would be really beautiful to understand this theoretically better than just do experiments, but this is hard questions, I think. And also you have even different numbers of local minima, and they can be bad. They can be non-global. And we did some experiments, as I said, but I don't know an average number or something of local minima or critical points. Yeah, and so that was somehow what I wanted to end with. And maybe give you one last primer on, it would be really nice to have some closed formulas for these generic ED degree of determinantal varieties, but I don't know any closed formulas that only depend on the size of the matrix and the rank. So if you compare these two formulas with each other, you see, yeah, the ED degree is easy, but then this generic ED degree is like a mess. And I don't know a better way. If someone knows a closed formula or a better way of writing this formula, I think this would be interesting as an algebraic geometry challenge. Okay, and with that, I want to end my talk, and yeah. Thanks for the questions already.
Thanks very much, Kathleen. And again, sorry for the confusion.
Yes, there's no problem. It was quite fun, maybe refreshing wake up.
Yeah,
everyone, I don't know.
I have two time zones on my laptop, so I got
yeah, I
confused.
understand. I understand.
We still have some time for questions.
Hello, Kathleen.
Hi, Emre. Nice to hear you.
Very nice talk, thanks. I wanted to ask you, so this, of course, you're talking about these linear networks, but in practice, we do want to introduce some nonlinearity. And I just want to ask, I mean, what's your intuition? Let's just put some polynomial nonlinear functions in between or something. So how much can you generalize from what you're talking about?
Yeah, have you been at the talk by Joe Khalil
Yes,
yesterday?
that's exactly what I'm saying.
Right, so that's somehow, I mean, I think Matthew, who is our common co-author, and John Bruno, so I think these projects happened roughly at the same time in parallel, and we did chat with each other. And I mean, I think like much more can be done and understood. I mean, the questions are difficult, but I think, yeah, I don't know, the paper of Joe and Matthew is a good start, but there was much more open questions. Yeah.
I mean, because your Euclidean distance degree for linear maps from jumping from 3 to 39, I mean, that just indicates that this is sort of an insanely special case, but is it just for linear maps, or is it?
Oh, you mean that specific part?
For instance, yeah.
I think it is also special in this, Joe, maybe if he's here, he can correct me. I think it's also special in these polynomial case that Joe explained, because there, at least like in somehow the first baby cases, this manifold was then related to tensors instead of matrices. And also there, if you have a special embedding of your tensor variety, then that also gives you a special AD degree then in comparison to a generic embedding of the variety. I think, so at least in this baby case, this should still be true.
I see, thanks.
Edward, do you have a question?
Yes, hello and thank you. It's probably a bit of a stretch, but maybe you know how to do it, or maybe you've seen someone do it, like given you spoke about functions and their critical values. Has anyone tried to do some Morse theory in this setting?
I have been asked this question before, actually. I forgot by who it was, though. I have not seen, I think, a talk or paper recently about this, but I had a conversation. I don't know. I don't want to say anything wrong. I don't know. I have to check my emails and get back to you.
All right, thank you.
Any other question? If not, let's thank Kathleen again. And thanks very much for both the interesting talks actually in this session.